Welcome to the Spartan-7 Overview Technical Module. My name is Nick Mehta. I'm a Senior Technical Marketing Manager. I'm going to take a quick look around the Spartan-7 architecture to familiarise you with the technical capabilities of the family. Okay, so let's get started. Spartan-7 FPGAs are built on the established 28 nanometer 28 HPL process from TSMC that has been so successfully used for the existing 7 series FPGAs. This process really enables an excellent balance of performance and power consumption, providing the best performance per watt. The architecture is targeted to be able to handle high-performance applications at a low total cost, i.e. cost of device, including the small form factor packaging, cost of tools, and cost of resources to create the user design. Targeted to applications with limited available PCB footprint, such as sensor interfacing, communication bridging, and motor control. So let's take a look at the family table. Here is a simple look at the Spartan-7 family in a datasheet style table. You can see that the family ranges from 6,000 to just over 100,000 logic cells. All devices contain slices of logic and DSP, with up to 160 DSP slices, and block RAM with up to 120 block RAMs or 4.2 megabits of block RAM. And finally, up to 400 I/O in the largest device package combination. Of course, this is only a small section of the family table. The full device resources are available in DS180, the 7 series FPGAs overview on Xilinx.com. Here's a look at a typical floor plan of a Spartan-7 FPGA. I've included here a little legend to show what we're looking at. So starting at the far left and right, there are two columns of I/O shown in light grey. These are adjacent to the clock management tiles shown in dark grey. And sticking with the dark grey, we have the central vertical clock spine in which the vertical global clocks are routed and the global clock buffers reside. The device fabric consists of columns of logic, DSP and block RAM, which are divided into clock regions. Each clock region is half the width of the FPGA and a fixed height that equates to 50 rows of CLBs or 5 block RAMs or 10 DSP slices. There are between 2 and 8 clock regions per Spartan-7 FPGA. The logic structure is core to all FPGAs. In Spartan-7 FPGAs, 6-input lookup tables, or LUTs, are combined with 2 registers. There are 4 LUTs and 8 registers per slice, with 2 slices making up a CLB. So slices come in 2 styles, slice L, in which LUTs are capable of performing logical functions, and slice M, in which LUTs are capable of performing logical, shift register and distributed memory functions. Approximately 30% of the slices in Spartan-7 FPGAs are the memory-capable slice M. Here is another datasheet style table showing the quantity of slices, registers and distributed RAM or LUT RAM in each of the family members. You can see the smallest family member contains 938 slices, just over 7,500 registers, and can be configured as 70 kilobits of distributed RAM. Then up to the largest there are 16,000 slices or 128,000 registers, and it can be configured as just over 1 megabit of distributed RAM. For larger storage than distributed RAM, there are blocks of block RAM, each 36 kilobits in size, that can be split into 2 totally independent 18 kilobit RAMs. There are 2 ports that address common data, allowing the block RAM to be configured in true dual port, simple dual port or single port modes. In the dual port modes, the 2 ports can have different port widths and can have different clocks from one another. To facilitate crossing of clock domains and various other functions, every block RAM has built-in FIFO circuitry that enables every block round to be a configurable FIFO. Additionally, to ensure integrity of the stored data, there is integrated Hamming error checking and correction capability. So it's capable of detecting double-bit errors and correcting single-bit errors in the memory array. So here we can see the quantity of memory in the Spartan-7 family, ranging from 180 kilobits in the smallest device up to 4,320 kilobits, or about 4.2 megabits, in the largest device. All Spartan-7 FPGAs have many dedicated, full custom, low-power DSP slices, combining high speed with small size. The DSP slices enhance the speed and efficiency of many applications beyond digital signal processing, such as wide dynamic bus shifters, memory address generators, wide bus multiplexers, and memory-mapped I/O registers. Key features include a 25 by 18 2's complement multiplier with dynamic bypass, a 25-bit pre-adder for saving power and reducing resource utilization in symmetrical filter applications, a 48-bit accumulator that can be used as a synchronous up-down counter, a single instruction multiple data or SIMD arithmetic unit with either dual 24-bit or quad 12-bit add, subtract and accumulate, a pattern detector capable of convergent or symmetric rounding and 96-bit wide logic functions when used in conjunction with the logic unit, and optional 17-bit right shift to enable wider multiplier implementation. Here we see the DSP resources available in the different Spartan-7 FPGAs and what this equates to in terms of performance. So to calculate these performance metrics, we assume a symmetric FIR filter using the pre-adder. So, moving on from the fabric, let's look at how the clock signals reach the various different clocked elements. Clocks can either come into the device from an external source or be generated internally from one of the clock management components. For external clocks, there are clock-capable I/Os in the I/O banks. These CCIO pins allow clock signals to be driven directly onto the clock network and onto the clock management components in the CMTs. The CMTs contain one MMCM and one PLL each. The MMCM is the primary component for generating clocks for the fabric, and the PLL is generally aimed at memory interface clocking. However, both MMCM and PLL can be used to clock the fabric. Just be aware whether or not the PLL will be required for a memory interface before committing it to the fabric for fabric clock generation. Once the clock signals have entered the device or been generated, they need to be routed to their destinations. The diagram shows a device here with 4 clock regions. The vertical clock spine in the middle of the device is the boundary between the left and the right clock regions. This vertical clock spine contains the global buffers, or the buff-G, that route the clocks throughout the FPGA. To get onto the horizontal clock routing in the middle of the clock regions, there are horizontal buffers, or buff-H. The clocks then reach the registers, DSP, etc. from these horizontal clock routes. So looking here at the datasheet style table, you can get a feeling for how many of the different clock resources and clock regions there are in each of the different Spartan-7 FPGAs. In Spartan-7, the I/Os are arranged in banks of 50. They're classified as high range and are capable of single-ended or differential communication up to 3.3 volts. Each I/O block contains uncalibrated split termination that creates a Thevenin equivalent circuit using 2 internal resistors which, when activated, they reduce reflections and ringing on PCB traces, thereby maintaining signal integrity. The output slew rate and drive strength can both be programmed to one of several values. Slew rate can be fast or slow, with the default being slow. Fast slew can be used for high-performance applications, but it needs to be designed properly to avoid increased noise or reflections. Different output drive strengths can be used to cater for the needs of the driven or the downstream device. The default drive strength is 12 mA, but depending on the I/O standard used, can be reduced to 4 mA for the lowest power, or increased to 24 mA for the strongest drive. As well as the physical I/O block, the I/O bank contains I/O logic resources for manipulating incoming and outgoing signals. The input delay, or I delay, is a 31-tap wraparound delay primitive with calibrated tap resolution, and it's used to delay incoming signals on an individual input pin basis. So if we look at the I/O performance in the form of the maximum LVDS rates, it's clear to see that despite being relatively small, low-cost devices, Spartan-7 FPGAs are capable of operating at very high performance, in this case well over 1 gigabit per second. So just to take a brief look at the specific capabilities of the high-range I/O, here is a table showing the primary I/O standards, their variants, operating voltages, and permitted drive strengths. As you can see, there are many different standards supported by the high-range I/O, from 1.2 up to 3.3 volts, with drive strength from 4 mA up to 24 mA. This vast array of standards enables Spartan-7 FPGAs to provide any-to-any connectivity, connecting a multitude of system components together within a single device in a single package. In addition to the large quantity of data that can be transported over the I/O, Spartan-7 FPGAs also contain dedicated physical layer circuitry for implementing memory interfaces. So each I/O bank is tightly coupled with a clock management tile. And within the clock management tile are the components needed for implementing a memory interface up to by 32 DDR3 at 800 megabits per second. The high-performance programmable logic in Spartan-7 FPGAs can operate at sufficiently high frequencies to enable soft memory controllers, avoiding the reduced flexibility and constrained I/O placement associated with a hard memory controller. Looking at the datasheet style table, you can see the supported memory interfaces, the standards, and their data rates at the supported speed grades. So memory controllers built in the programmable logic can be half rate or quarter rate. In order to meet the demands of the cost-sensitive market, Spartan-7 FPGAs come in a variety of small form-factor, low-cost packages. These small packages are vital for the products to fit into some of the tight spaces that their target applications require. You can see from the table here the Spartan-7 family provides the only 28nm FPGA in an 8x8mm package. For more information on the device and package combinations, please refer to DS180, the 7 Series FPGA's overview. The Spartan-7 7S25 to 7S100 contain the flexible analog interface called XADC. XADC consists of two 12-bit 1 megasample per second ADCs, each with separate track and hold amplifiers, supporting a range of analog input signal types, including unipolar, bipolar, and differential. An on-chip analog multiplexer can multiplex up to 17 external analog input channels, and the on-chip voltage supply and temperature sensors provide accurate readings for both die temperature and power supply voltage, all enabling the compliance with reliability standards such as FIPS 140-2 and IEC 61508. So now we understand the device capabilities, let's take a look at the device performance. As mentioned, Spartan-7 is built on the 28HPL process, providing high performance and great performance per watt. For example, the by 32 DDR3 interface at 800 megabits per second provides up to 25.6 gigabits per second of memory bandwidth. And the 160 DSP slices operating up to 550 MHz provide symmetrical filter performance up to 170 Gmax. This is obviously only a small excerpt from the datasheet. For the full quota of datasheet parameters, please see DS189, the Spartan-7 FPGA's datasheet.